Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 22, practice session number 4, in which we will solve our next problem, number 24, in which I titled Verbal College Entrance Exams for the following reasons. Back in the 1980s, Moscow, then USSR, and for several decades actually prior to that, the system of college entrance exams into the top tier schools was based on the so-called sudden death or elimination on the first failure approach, and the overall college entrance exams consisted of 3 parts: the examination in mathematics, the examination in physics, and the examination in literary arts, which amounted to writing a composition based on a given prompt. Now, the examination in mathematics and physics went in this particular order: mathematics first, physics next, because mathematics is a foundation of all the technical disciplines. And if you fail the exam in mathematics, there was no point to proceed any further. And each of these examinations in mathematics and physics consisted of 2 parts: the written exam and the verbal exam, both in physics and in mathematics. And the sudden death or the elimination on first failure approach meant that you had to succeed at all the exams, of which in general you had to take 5. There were several exceptions to this, but in general 5 exams: written mathematics, verbal mathematics, written physics, verbal physics, and then a composition for a given prompt. 5 exams, and you had to succeed on all of them. If you fail any one of these examinations, at the point of your failure, you were eliminated from the candidates pool, and for that college for this year, the game was over for you. You either could wait another year and reapply and take the entrance exams again, or you could go and take the entrance exams for the lower ranking schools, because the top tier schools had held their examination sessions in July, and the lower ranking schools had their exams sometimes in August. So you had time to switch gears and apply to a lower ranking school if you failed any of the examinations for the top tier school. Now, the written examination in mathematics and in physics actually worked in the same way. You were given, let's say, 3 or 4 problems, and let's say 3, 4, or maybe 5 hours, and you had to turn in all the sheets on which you solved all the problems, or the solutions of all the problems that you managed to solve. And the solution had to be laid out in a step-by-step fashion, blow by blow. You had to tell the story of how you obtained that solution with all the intermediate calculations, because the admissions committee wanted to see 2 things. They wanted to see how you think, and wanted to see how you think. And sometimes, on a very rare occasion, of course, you could get some credit for a problem that you did not solve, but you demonstrated or showcased a very original line of thinking or an originality of thought. That was the written examination, and these examinations were, of course, held several days apart. If you sit through, let's say, written mathematics exam, then several days later you would come to that college. By the entrance, there were printed out sheets of paper on which the last names of people who made it through the written examination were displayed. You will come in, check your name is there, then you will be allowed to sit through the verbal examination. If your name is not on the list, then again, for that school, for that year, the game is over for you. You have a decision to make. And then several days later, you will do the same thing for the verbal examination. Take the verbal exam. If you didn't make it, your name will not be on the list. If you made it, you can proceed to the next round, and then written physics, verbal physics, composition on a given prompt, and so on. So if you take successfully all the exams, then your chances are high that you will get in. As soon as you fail, you're eliminated for that school for that year. Now, during the verbal examination, the examiner had the right to deep dive into any topic that was relevant for this particular problem that you chose at random. The examiner could not quiz you on everything that, let's say, elementary mathematics is, but any topic that was relevant to the problem that you were solving and that you chose was a fair game. Again, the verbal examination meant face-to-face in real time. You develop your solution step by step, blow by blow, and at any time the examiner could tell you hold your horses, explain why you made this conclusion, give an alternative reasoning, maybe prove something another way, and deep dive into the subject matter deeper and deeper. And this brings us to the title of this episode. In this episode, we will solve a problem that is a typical representative of such a verbal mathematics college entrance examination. These problems were usually not as difficult as the problems that were given during the written exam, but still the pressure is high. Students or potential students, hopeful students, are nervous. So in order to get your wits about, the problems were not that difficult, but still challenging enough. And as such, in the problem number 24, this is not the problem 23. The problem 23 we solved in the previous episode. In the problem number 24, we are given two fixed coplanar circles that touch each other externally. And for definitiveness and without the loss of generality, we will assume that the length of the radius RA of the circle SA is strictly smaller than the length of the radius RB of the circle SB. And we're also told that we're given a common external tangent of these two circles or a straight line L. And in this problem, we are given two objectives. The objective number one is to come up with the Euclidean tools only, a straight edge and a compass algorithm for inscribing a circle into the planar region or a curvilinear triangle trapped between the two externally tangent circles SA and SB and the straight line L that plays the role of the common exterior external tangent for these two circles. We want to know exactly how this circle can be inscribed. We want the steps. And the objective number two is to find a relationship between the lengths of the radii of the circles SA, SB, and SC. The radii RC for the length of the radius of the circle, inscribed circle RC, RA, the length of the radius of the circle SA, and the length of the radius RB of the circle SB. Ideally, if we torture this relation enough, we can express it as a function of the length of the radii RA and RB of the circles SA and SB. Before we deep dive into the solution of the first part of this problem, I want to apologize to my audience. I double-checked my records. Meanwhile, this is the problem number 23, not 24. Disregard my previous comment. Now back to the problem. When I was solving this problem, the way I solved it is as follows. This is not, as a hint, this is not the only inversion that solves the first part of this problem. This is a choice, and I will leave it as an exercise to the viewer to figure out which other inversions will solve this problem in an elegant way. But the way I went about the solution of this problem is the following. Let us concentrate on the point of external tangency of the given circles SA and SB. That is the point that we will call T for tangency between the circles SA and SB. This will be TAB, this point right here. We already know that when a circle passes through the center of inversion, then according to the theorems that we proved, that circle under the inversion of the parent plane will be taken into a straight line that does not pass through the center of inversion, regardless of the power of inversion, positive or negative. That will happen, and the other way around. A straight line that does not pass through the center of inversion will be taken into a circle that does pass through the center of inversion. As such, we make the point of external tangency of the two given circles, TAB, as the center of inversion, and it will be with positive power, plus r squared. Power is positive. Then let us put together a little demonstration over here. So let's say this is our smaller circle, this is our larger circle, this is a straight line, L. The two circles that touch at this point will be taken into what? They will be taken into, let's draw their images with a chalk of different color. If the point of external tangency of these two circles is chosen to be the center of inversion, then under the inversion of the parent plane with respect to a circle that is centered at that point and it has any non-zero radius. And here again, remember, in one of the first lectures of this course, I observed that many times the actual length of the radius of inversion is irrelevant, and this is precisely the case. I put together a small demonstration for you at the end of the segment, but for now I will not even show the circle of inversion because it is really not relevant. The only thing that is relevant is the center of inversion, the point of the external tangency of these two circles, and the power of inversion, which is positive, and we have plenty of information to go on. The angle between these two circles is the angle between their tangents at the point of contact, because the common internal tangent in this case degenerates to, in general, distinct internal tangents degenerate into just one that will go this way. It means that the angle between these two circles is, well, actually technically it comes from a countably infinite set of integral multiples of pi, of which 0 is a very convenient and pleasant representative. That means that the common tangent to these two circles, two tangents merge into one. The angle between them is 0. In some sense, these two tangents are parallel, and in some sense, these two circles are parallel. And that means that under the inversion of the parent plane with respect to that point of tangency, these two circles will be taken into two straight lines that will not pass through that center of inversion, but which will have the same magnitude of the angle between them. And because in this case circles are taken into straight lines, the image straight lines will be parallel to each other. This is the important observation that we have to make. Again, let's say our circles are taken into the straight lines like so. This is our circle SA, this is our circle SB, this is our circle S prime B, which in this case is a straight line, and this is our image of the circle SA, S prime A. Depending on the size of the radius of inversion, the location of this straight lines will be varying, but the fact that the straight line S prime A will be parallel to the straight line S prime B will not change. Again, we remember that inversion preserves the magnitude of the angles between the cooperating curves, and it reverses the orientation or the direction of this angle to the opposite. That is why inversion is the so-called anti-conformal mapping of a plane. In fact, it's a real or complex plane into itself. And what else will happen over here under this inversion? In other words, our circle, genuine circle SA, will be taken into a straight line, S prime A, and our circle SB will be taken into the straight line S prime B, and the straight lines S prime A and S prime B will be what? They will be parallel. And look at this. The straight line L that plays the role of the common external tangent of the given circles SA and SB will be taken into what? That straight line does not pass through the center of inversion. That means that that straight line will be taken into a circle that does pass through the center of inversion. In other words, the straight line L will be taken into the circle L prime such that the center of inversion, the point TAB, will precisely sit on it, or that circle will pass through the center of inversion. Let's say somehow it goes like this. It will pass through the center of inversion. Now, what other interesting properties will we have for this circle L prime? Well, remember that when the cooperating curves touch, then their tangency points under any inversion of the parent plane are preserved. That means that if the circle SA touches the straight line L, it means that the image of the circle SA will touch the image of the straight line L. And that means that the straight line S prime A will touch the circle L prime. Likewise, because the circle SB touches the straight line L, it means the images of these two objects will also touch. The image of the circle SB is the straight line S prime B, parallel to the straight line S prime A, and the image of the straight line L is the circle L prime. And that means that under the inversion that is centered at the point of external tangency of the generating circles SA and SB, under that inversion, the straight lines S prime A and S prime B will sort of squeeze in between them the image of the straight line L, the circle L prime, which will touch these straight lines at a couple points, which are actually the images. Of course, I have a goofy by hand rendering of the situation, but you understand that the points of tangency will be the images of each other under the chosen inversion. And let's say if, again, we will be solving this problem in reverse order, then that means that we will assume that somehow the sought after circle S prime C will be already inscribed somehow in the place where it's supposed to be inscribed, right here. Now, under the chosen inversion, what will happen to that circle if we temporarily assume that, let's say, the mathematical oracle somehow gave us that circle and it is wonderfully inscribed into the curvilinear triangle trapped between the given circles and their common external tangent, and it touches the circles externally and touches the straight line L at some point. Where will that circle, the sought after circle, which we temporarily assume is given to us, be taken under that inversion? Well, that circle by the demand must touch three geometrical objects at once. It must touch the circle SA, it must touch the circle SB, it must touch the straight line L. And since we know that under any inversion of the parent plane, be the power of that inversion positive or negative, the tangency points are preserved. What does that mean? That means that the image of that circle will also touch the images of all three given objects under that inversion. We know the images of these three given objects, two parallel straight lines and a circle. So what kind of observation we can make that will, in a sense, unlock the solution of this problem? Well, the observation that we make here is the following. The image of the straight line is the circle L prime. The images of the circles SA and SB are the straight lines S prime A and S prime B that are parallel. And the image of the sought after circle SC, let's see, I'll write it down in small font, but hopefully you guys see it, the circle SC right here, this guy, will touch all three objects at once. It must touch the straight line S prime A, S prime B, and it must touch the circle L prime. Here, and I recommend that you all go through this exercise, use your favorite graphing software, and go through these manipulations by yourself to see how they work. You will have a choice. This circle, in a sense, once you work backwards, can be located on that side of the center of inversion or on that side. Here we want to go on this side, and that means that the image of the circle, let me even write it down here like this, our circle SC, which we temporarily assume has been constructed, we do not know how yet, but we assume that it will be taken into another circle, S prime C, because that circle does not pass through the center of inversion. Remember, in this case, we proved a bunch of theorems that show that the circle will be taken into a genuine circle, and it will be also squeezed between the parallel straight lines S prime A and S prime B, and it will touch the image circle L prime. So this circle will go like this. You see, this is the tactical observation. This is the circle S prime C. In some sense, of course, this point of tangency, they must be collinear, but you understand what's going on. And look at this wonderful situation that we can have in mathematics, which is really bewildering, both bewildering and absolutely amazing. In the original difficult to solve problem, we have seemingly two distinct objects, a circle, which we are required to construct, and a straight line. They're very different. But under an appropriately chosen inversion or a transformation, what do we have? The circles L prime and S prime C are what? They're almost identical or almost isomorphic, which means that they are equal in a sense that their diameter and their radii are exactly the same, equally sized circles that are trapped between two parallel straight lines and touch them. And in that respect, we now know how to solve this problem, because by making a temporary assumption that the sought after circle is given to us, we reason in reverse order from the solved state to the unsolved state. Now, if we remove this circle from the picture, but we know how to construct the circle S prime C with the Euclidean tools alone, we can generate the traditional forward flow of causality solution, which amounts to what? We basically, we can frame a problem like this. How do we construct a circle S prime C that is tangent to two given straight lines and touches the circle that is also trapped between these two parallel straight lines? Well, that task is basically trivial. First, we construct a straight line that runs in the middle of these two parallel straight lines. It will be this straight line right here somehow. And this construction is very simple. Pick a random point on a random line, straight line, S prime B or S prime A over here. Construct a perpendicular to it. This perpendicular will intersect the other straight line at some point. These 2 points will delineate a line segment. That is the Euclidean distance between these two straight lines. And the perpendicular bisector precisely will be a median straight line that is equally distant from both parallel straight lines. And that straight line will house both the center of the image circle L prime and the center of the circle S prime C. Now, that median straight line will intersect the image circle L prime at two distinct diametrically opposite points, of which we take the appropriate one. We have to carefully choose which one. Here, we take the one that is further away from the center of inversion, this one. And then when we constructed this median, we know this distance. This is the radius of the circle L prime. So here, centered at the point where the median intersects the image circle L prime here, we construct a helper circle of this radius, and boom, that helper circle will mark the spot where the center of the image circle S prime C will be. Then we draw the circle, reflect it in this center, and voila, we have our sought after circle SC that will be inscribed the way it is requested to be inscribed in the curvilinear triangle. And now that we understand how we generated this solution, we can formalize it and write up a formal algorithm. But it's important to understand that we solved the first part of this problem by combining the so-called transform and conquer problem solving approach, transform and conquer, where we took a difficult to solve problem, rearranged it or transformed it into a setting where the solution became trivial, and then we took the solution of the transformed problem and applied the reverse transformation to it, or inversion in the same center with the same power. And we also use the reverse order problem solving approach when we temporarily assumed that the sought after object is given to us. Then we arrived at the situation where we could remove that object and generate the forward flow of causality and take our situation, our problem, from the unsolved state to the solved state. And now we can write up a formal algorithm for the objective A. In the demonstration that I put together for you using the free software called GeoGebra that you just saw a few seconds ago, I wiggled the radius of the circle of inversion back and forth, and you saw that the corresponding parallel straight lines into which our generating circles SA and SB are taken, they dance around in some interesting way. The circle that is the image of the straight line out also dances around squeezed as in the vice between these two straight lines, but amazingly enough, the sought after circle SC that we're required to construct actually stays one and the same, because precisely again, all the given objects are fixed. The location and the size of the circle SA is given and fixed. The location and the size of the circle SB is fixed. Consequently, the location and the size, well, specifically the location, the juxtaposition of the common external tangent is fixed, but the circle, the inscribed circle SC is also fixed. It remains where it is, despite the fact that I wiggle the size of the radius of inversion, and that was the objective, the goal of my demonstration that I put together for you. This time it was not an animation. I wiggled with the mouse the point that controlled the length of the radius of inversion, and the whole idea here is that I picked with my solution, I picked the point of external tangency TAB as the center of inversion. And the idea here is that, yes, in the format of real-time face-to-face verbal examination, you are nervous, a lot of writing on that particular moment, but you have to keep your wits about and realize that this is one of the possible solutions. If you have the intellectual bandwidth, then you can actually tell the examiner that you think that this is not the only inversion that solves the problem in an elegant way. The first part of our problem, other inversions will work. Again, I will leave it as an exercise for you to figure out what is the center of inversion. The power of inversion could be positive, but as a hint, again, we suggest that you put this video on pause, walk away from the computer, try to solve this problem on your own, generate this idea on your own, then come back, compare your ideas to ours. But the interesting points over here are the points where the given circles touch the common external tangent. See what happens if you play with these 2 points. Now that you understand how we solve this problem, the combination of transform and conquer and reverse order, we temporarily assumed that the object sought after is given to us by, let's say, a mathematical oracle. We make this assumption without knowing how that object was actually synthesized, but taking the solid state as the input, as the fodder. We unwind the steps in reverse order, then we realize, aha, this is how we can solve this problem if we start reasoning in the traditional or requested sought after forward flow of causality order. And this is the algorithm that we come up with for one solution. It's not a unique solution, but one solution that definitely works. We pick the point TAB, the point of external tangency, as the center of inversion. We take the power of inversion to be positive, and we reflect all three given objects that are given to us. The circle is A, the circle is B, the straight line L, that is a common external tangent to these two circles. And we reflect these three objects in the circle that has the point TAB as the center, and any radius that is greater than 0, that is why I did not even specify what this radius is. It's irrelevant, and the proof of the fact that it's irrelevant is in some sense a visual demonstration of that fact. That was the point of this demo that I put together for you with GeoGebra. So we take the circle SA into a straight line S prime A that will be parallel to the straight line S prime B, which is the image of the circle SB. The straight line L is taken into a circle that passes through the center of inversion. Then we construct, I call it, it cannot be called a bisector, but let's say, median straight line that runs in between B, the straight lines S prime A and B in such a way that B is, over here I hijacked the notation, the distance between the straight line, the median straight line, and the straight line S prime A is the same as the distance between this straight line and the straight line S prime B. This straight line will intersect. Remember that this is S prime A, this is S prime B, and let's say this is what the B is, equally distant from these two straight lines and parallel to them, evidently. But this straight line will intersect the circle L prime at two distinct points, here and here. We pick the right one. I put over here the point Q and point X. We choose the right one, the one that's further from the center of inversion. Play it by ear, see how these things play out. This is the point, and we use this point as the center of the helper circle that will mark the center of the actual reflected circle. So helper circle H centered at the point Q with the radius that is equal actually to the radius, let's put it this way, it's radius of the circle L prime, half the distance between the median straight line B and any of the parallel straight lines S prime A or S prime B. That circle will intersect the straight line. I made a mistake here. Straight line, our straight line B, again at two distinct points. This will be the point, let's say Y. Here at the bottom, you cannot see it, but it's here, the point O. We pick this point as the center of a circle that has the same radius as the radius of the image circle L prime. Half the distance right here, this is half, this is half. That's the radius, and voila, we have our circle S prime C, and then we just reflect the circle S prime C into the sought after circle. This is the sought after circle, and in many cases, our reasoning that led to the solution is pretty much a proof. It can qualify as a proof, because in reality, after you're done with the constructive steps, with the presentation of an algorithm, that presentation has to be followed by a proof that this algorithm is correct and does indeed produce the object sought after and not some other wild animal. But again, our line of reasoning that we presented prior, transfer and conquer, reverse order, is pretty much such an acceptable proof. And again, we recommend that you use your favorite graphing software in order to go through these steps and actually construct that circle yourself, and one more time put through your mind the theorems that we proved that are used in order to come up with that solution. And we will move on to the second part of the problem 23. If you are new to verbal examinations, then most likely you will feel uncomfortable at first, but the only way to deal with the ability to take verbal, real-time, face-to-face exams successfully is to practice solving problems. Once you gain the confidence in solving problems and sharing your solutions with others, then you will not feel uncomfortable anymore. And this all goes back to what we preach on our channel. Mathematics is an art of telling a story. If you are not telling a story, you are not doing mathematics. If you are telling a story, it remains to be seen whether you are doing mathematics or not. But the idea is that practice telling a story, and then hopefully you will be okay. For example, I personally, again, my personality is irrelevant. My personality has nothing to do with this channel. This channel is dedicated to an idea of practicing the art of hard sciences for the sake of practicing hard sciences. But I, for example, personally was exposed to verbal examinations since the tender age of 7. And once you are used to share your thoughts in a public setting in front of the class with a piece of chalk in your hand by the blackboard, then you will be fine. So now, as we move on to the second part of this problem, we need to recover a relation between the length of the radii RC of the circle that we just constructed and the length of the radii of the generating circles SA and SB. Again, we take it for definitiveness and without the loss of generality that one circle is strictly smaller than the other. That's the most interesting case. We can rename the circles. You want to make circle SA larger than the circle SB. Be my guest, it doesn't really matter. But the thing here is the following. We take A to be the center of the smaller circle SA, the point A. The point B is the center of the largest circle SB. And the orthogonal projections of these centers onto the straight line L will be correspondingly AL and BL. AL is the orthogonal projection of the center A of the circle SA onto the common external tangent L. BL is the orthogonal projection of the center B of the large generating circle SB onto the common external tangent L. C. Uppercase C is the center of the circle that we just constructed. And RC evidently is the radius. So here is the deal. We will basically solve the second part of this problem. Again, it's not too complicated. You just have to keep your wits about under the pressure of a verbal face-to-face real-time examination. But all the second part of this problem, B, or number 2, if you will, is basically a middle school application of the Pythagorean theorem in 3 different places and in 3 consecutive steps. And this is it. You just have to see it again under pressure of the verbal face-to-face real time, yes, but this is what you're expected to see. Lastly, if we project orthogonally the center, the point C of the circle SC onto the line segment AL, or on a radius of the smaller generating circle, then we will obtain the point CA, uppercase C with the subscript A. This way the angle is right, so we have the right triangle CA. C, and for this triangle, let's say we write it down as triangle A. C is right by construction, and from that triangle, based on the Pythagorean theorem or in his elements, Euclid builds up to that proof in book 1, proposition 47, if I'm not mistaken. 47 or 43? It's a prime number, 47, I think. So from this theorem, we express the length of the side CAC. This is what? This is the square root extracted from the square of the hypotenuse AC. The hypotenuse AC, and this time, is a composite quantity. Why? Because it again rides on a basic theorem from the theory of circles. The point of tangency between 2 circles lies on the line of centers of the tangent circles. Whether the tangency is external or internal doesn't really matter. The circle SC touches the circle SA, as we just explained and proved with the previous segment at this point right here. This point and the points A and C are collinear, so the length of the line segment AC is representable as the sum of the lengths of the radii RA and RC. So this is how we splice these guys into the works already. This is our hypotenuse, and from this square, what do we subtract? From this square, we subtract this delta. And this delta is the difference this time, not the sum, but the difference between the length of the radii of the smaller circle SA, RA, and this little piece right here is the RC. So minus square RA minus RC squared. So we can do this on the fly without much paperwork. Look at this. RA squared with a plus sign, RA squared with a minus sign, gone. RC squared with a plus sign, RC squared taken inside with a plus sign, but the minus in front, so gone. What is left over? The only things that are left over is twice the product of this radii minus twice the product. Minus times minus is a plus, plus and plus, 4 times the product. Square root of 4 is 2, so what do we have? 2 times RA times RC. It is that straightforward, and now we can write the distance from the point CA to C is twice the square root of RA times RC. The situation with the circle SB is not physically exactly the same, but structurally it is exactly the same as the situation with the circle SA that we just covered. That is, if we orthogonally project the center C of the just described circle SC onto the line segment BBL into the point CB, then the triangle B, not A but B, CB, CB, CBC will be what? Will be right at the vertex CB due to how this point was constructed. The projection is taken to be orthogonal. Then from the triangle this time BCBC, we have again by the Pythagorean theorem, the length of the side of this right triangle is the difference between the square root and is the square root of the difference between the squares of the length of the hypotenuse and length of the other side. The hypotenuse BC, again, is a composite quantity, is represented as the length of the radius RB of the generating circle SB and the length of the radius RC. So RB plus RC squared minus RB minus RC squared, exactly the same arithmetic. The squares are gone and the products are doubled. Square root of 4 is 2, and then we have our relation that is similar to the previous one. The length of the side CBC, this side right here, this piece, is twice the square root of the product of the length of the radii of the generating circle RB and the length of the radii of the inscribed circle SC. Likewise, the situation with the circles SA and SB is exactly the same as before. Structurally, it is the same. That is, if we project the point A, the center of the smaller circle SA, onto the line segment BBL, into the point AB, then the triangle BABA will be right at the vertex AB. And if you were to rename the circles the other way, if the circle SB was smaller and the circle SA will be larger, you will do the same thing, but you will project the point B onto the line segment AL. Again, that situation will be isomorphic to this one. It doesn't really matter. Structurally, nothing changes. We still have the same Pythagorean theorem applied to the triangle BABA, the right triangle BABA, this smaller triangle that sits on the very top. And according to it, the distance from the point AB to the point A is equal to the square root of the difference between the square of the hypotenuse and square of the other side. The square of the hypotenuse, BA, again, is a composite quantity. It can be represented as the sum of the length of the radii RB and RA, and this side over here, BAB, is what is the difference between the radii RB and RA. And in some sense, it can be actually even written the other way around because there is a square. It doesn't really matter, but it will reflect the fact that structurally the situation is the same regardless of which circle is larger and which is smaller. Again, the arithmetic is the same. R square of A minus R square of A cancel out, R square of B minus R square of B cancel out, minus times minus twice the copy, 2 copies of the product plus 2 another copy is 2 plus 2, 4, square root of 4 is 2, 2 copies of the square root of the product of the length of the radii RB and RA. This is our result. And now we can represent or use what fact? We can use the fact that the shape A, AB, BL, and AL is what? Is a rectangle. And that means that the length of the line segment A, B, A is the same as the length of the line segment AL, BL, just in case, but that side, the line segment ALBL, participates in the formation of the rectangle ALBLCB CA, or we can go directly with the rectangle AABCB CA. That is equal to the distance between the points CA and CB. And because this distance is composite, we can represent it as the sum of the distances CAC plus CBC, as is evident over here. The distance CACB between the points CA and CB is representable as the sum of the distances from the point CA to the point C and from the point C to the point CB. And we know right now, the reason we went through the previous 3 exercises is that we know all the distances, the distance ABA, the distance CAC, and the distance CBC in terms of the available material. And all we have to do now is inject into this relation shown on the bottom left of your screen the relations that we obtained previously. That is 2 times square root of the product RA times RB is the same as 2 times square root of RA times RC plus 2 square roots of RB times RC. These are the relations that we developed for this distance, and this distance over here. Now we see that non-zero real number 2 cancels out all over the place. We divide this result through, and now we multiply this relation over here by the following number: 1 divided by square root of R A times RB times RC. This is always possible because none of these real numbers is 0. Dividing by a non-zero number in this case is allowed. And what do we see? Over here on the left hand side, the square root of the product RA and RB will be gone. So what will be left over here is 1 over square root of RC will be equal to what? Here RA and RC will disappear, so we'll have 1 square root of RB plus 1 over square root of, easy to see, RA, and voila, this is our result. This is a relation that locks together the radii of the circles SA, SB, and SC, each of which touch each other externally and also touch the common external tangent L. And if examiner asks you, you can, or you should be able to easily in real time write the expression for RC as a function of the radii RA and RB. You can do it in your mind. You do not need paper. Square root of RA plus square root of RB over the product flip and square, so your RC as a function of the radii RA and RB will be equal to what? RA times RB divided by RA plus twice the square root of RA times RB plus RB if you have to, but that is not, I'm not sure if that's more revealing than this. In this form right here, we can now in a sense, we solve the problem 23 that was given to us in this practice session completely. And again, the reason we're doing practices is because we are solving problems, taking on problems that seemingly or at first blush do not have anything to do with inversive geometry, but upon closer inspection, it turns out that a skillful splicing of inversion into the problem helps us a lot, and that is how we practice applying the newly learned material to solution of technical problems. The problem number 23 solved completely. We know an algorithm for inscribing circle SC in this case. I suggested inversion that is centered at the point of common tangency between two circles, but other solutions exist. I suggest that you try these 2 points, A, L, and BL, see what happens, develop the solution from there. We know that the radii of these circles are locked into the relation shown over here. And now for some random mathematical butterflies, we can play careful games with the specific values for the numbers RC, RB, and RA, because in general, these numbers could be any non-zero, arbitrary non-zero real numbers. But if we dial in these numbers ever so carefully, then we can obtain a random mathematical butterfly. That is, if we carefully set the value of the radius of the largest circle to the positive unity, the length of the radius RB is equal to 1. The length of the radius of the smallest circle RA is 1 over 2 squared, or 1/4. Then, according to our theorem that we just proved, or a relation that we just put together, the length of the radius of the circle SC, the RC, inscribed in such a way that it touches both of the circles externally and the common external tangent L, will be, according to our formula, is what? 1 plus 2. It will be the reciprocal of the square. It means that if we take the reciprocal of this and square, the length of the radius RC will be 1 over 3 squared, or 1/9. Now, let's say we inscribe this green circle in such a way that it touches the larger circle still of unit radius and the just inscribed circle SC. We'll call that circle SD. Its radius will be RB and RC, 1 plus 3. Flip and square, you have for the length of the radius RD, 1 over 4 squared. See the pattern? 1/2 squared, 3 squared, third squared, quarter squared, and so on. Inscribe yet another circle in such a way that it touches the previous one, the straight line, the common external tangent, and the unit circle SB. So for this guy, we will have the same relation, RB and RD, 1 plus 4, flip and square, 1/5, and so on. You see the pattern already. So if we will continue this process indefinitely, this is just a thought experiment, and we'll keep inscribing smaller and smaller circle in this space over here and create a family of, let's say, green circles, then what we will have over here is the following sum. We'll have 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared plus 1/5 squared plus, and so on. If we continue this process indefinitely, this is actually the value of the so-called Riemann zeta function evaluated at the argument. Let's say I'll put a squiggly like this, 2, and this will be the infinite sum from n varying between 1 and positive infinity, 1 over n squared, and that is equal to famously pi squared over 6, we compute the value of the sum on this channel using Cauchy's residue theorem and the contour integration in the complex plane by capitalizing on the fact that the corresponding integral is the sum of residues. We construct a special function, manufacture the residues that match this term right here, and compute this sum. But the utility of this observation and why it is a random mathematical butterfly is the following. You will come across random mathematical butterflies the more you work with different vaguely defined layers of mathematics. You will see results that look similar from seemingly disparate layers of mathematics, and that's what it is. The elements, the argument of the Riemann zeta function is the power into which reciprocal whole positive number is raised 1 over n. And this way, the reason this is a random mathematical butterfly is because we have a way to visualize and geometrically interpret the elements of that sum or the constituents of the Riemann zeta function evaluated at the argument 2. If we put this radii together, then we have the radius of length 1. Then we have, what was it? The length of the radius, it goes like this. 1, 1/2. Then we have 1/3, 1/4 squared, 1/5 squared, and so on. All these little line segments are precisely reciprocal squares of consecutive whole positive numbers. So if that is any help in visual comprehension of what is going on over here, this is a geometric model, one geometric model of the elements that make up the Riemann zeta function evaluated at the argument 2. And if we continue this process indefinitely, we sum all these line segments, we know that this number comes out to be pretty finite, pi square over 6. And realize here that we always inscribe our circles in such a way that they touch the circle RB all the time. But we can go in the opposite direction. We can always inscribe our circles in such a way that they touch the smallest circle, SA. So here, I wrote it down for you that the radii of the 3 initial circles is the same, but then if we inscribe the circle RD instead of touching the circle SB, touch the circle SA, then its radius will be expressed by the radius of the circle RA. And then we'll have 2 plus 3, 5, flip and square, take the reciprocal and square, 5 square. And then the next one, this circle right here, it will touch the previous circle, SA, still SA, so it will be 2 plus 5, 7. So flip and square, 7. So here we will have the following sum. It will be 1, let's say, if we grab the first one, 1 plus the circle that we inscribed, 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared plus so on. You understand what's going on? 1, 3, 5, 7. So here we will have another infinite sum that runs this time from 0 to positive infinity. But these are the squares of the reciprocal odd whole positive numbers. Sum of 1 over 2n plus 1 squared, and varies from 0 to positive infinity. When n is 0, we have 1. When n is 1, 3, and so on. And that number is evidently pi square over 8. We can easily compute the sum of reciprocal even numbers, 2n. 2 squared, 1/4, so the arithmetic is quite simple, but that is one interpretation. Again, that here we notice that when we inscribe this family, the yellow family of circles, if you will, we always want to touch the smallest circle as A, and this is it for the problem 23.